Hi everyone, welcome back to the series. So we're continuing our look at one-to-one functions. So in the previous video we saw what it means for a function to be one-to-one. Okay, we saw that it has to have passed the horizontal line test. Okay, or in other words, that for each y value, your graph has only one corresponding x value. Okay. Now, we saw in the last video also that for example, the parabola, the normal parabola that you draw, that's not a one-to-one function. Okay. So if I look at another kind of parabola, let's look at this one here. So we've got this function f, sorry, f of x equals x minus 2 squared. We're going to ask the question, is it one-to-one? Well, look at the domain. The domain is all real numbers. Okay, if we were to sketch this, this would be the parabola that has a vertex or a turning point at x equals 2. And it hasn't been translated vertically, so it's still on the x-axis. So let me use another color. Okay, so your parabola is going to look like this. Okay, it's just the parabola that's been translated 2 units to the right. Okay, and that is 2, 0. Now, because the domain is all real numbers, this graph goes on forever in both directions. So very obvious that it's not one-to-one because it doesn't pass the horizontal line test. So I can use a horizontal line here, it intersects there and there. Definitely not one-to-one. Okay, so does not pass the horizontal line test. However, is it possible for us to split this graph into pieces so that each piece that we split it into is one-to-one? Okay, have a think. Is there somewhere where we can split this into pieces so that each piece is one-to-one? And you might be thinking, well, probably, yeah, probably this point here, if we split it down the middle through its vertex, we'll get 2 pieces. Okay, we'll get this right-hand piece, which you would have seen in the previous video. You also get this piece on the left. Okay, and each of those pieces would pass the horizontal line test. Okay, so we can split this graph into 2 parts. Now, how would you sort of write this out? Okay, well, what you would do is you would just have to write out 2 separate functions. Okay, each of these functions have the same rule. Okay, you're going to make the rule y equals x minus 2 squared because that's what you want to draw. But you're going to have different domains. Okay, so for the left-hand piece in this picture, that would have a domain from -infinity to +2. And the piece on the right would have a domain from 2 to +infinity. Okay, each of them still has the same rule though. So what you would do is something like the following. You would say G would be, let's call G the left-hand piece of this parabola. So it has a domain from -infinity to 2. You can include 2 if you like. And writing the rest of our function notation, we'd have g of x equals x minus 2 squared. Okay, so it has the same rule because you want the parabola to look like this, except you want to stop drawing it once you get to 2, and that's indicated here by the domain. Okay, so that would be the left-hand piece of this parabola. It would look like that. Okay, alternatively, you could write something similar for the right-hand piece. And let's call that h. So we'll go h. The domain would be from, well, we can include 2 going up to +infinity. And our rule is still x minus 2 squared. Okay, except the domain is different. So your domain would be from 2 up to +infinity. So that would look like that. Okay, and if you sort of to draw both of these functions on the same graph, they'd connect up and give you your original parabola. Okay, so what we can do is restrict the domain of a function that isn't one-to-one. We can restrict it in such a way that we produce a one-to-one function. Okay, each of these graphs are now one-to-one functions that have the same rule as this original function that wasn't one-to-one, simply because we restricted the domain. Okay, so let's have a look at another example. We've got another parabola. So we've got f of x equals x squared minus 2x plus 4. And because the domain hasn't been told to us, we're assuming that it's the largest possible domain, which is all real numbers. Our job here is to write two functions with restricted domains such that each is one-to-one with the same rule as f. Okay. Now think about how we did that in the last example. Okay. The only bit of information that we needed to know was where your function needed to be split in terms of its x value so that it produced two one-to-one functions. And that, for a parabola, is at the vertex, at the turning point. And we don't even need to know the y value of the turning point. You just need to know the x value, because that x value is what you're writing when you restrict the domain. Okay, so it suffices for this example here for us to just work out what the x value of the turning point is going to be. We don't need to know anything else. We just need to know that spot, which is where we're going to split our function into pieces. Okay, so you might remember for parabolas that are written in this standard general notation, we can work out the x coordinate of the turning point by using negative b over 2a. Okay, in this case, b is negative 2, so we'll have negative 2 over 2 times a. A is 1, coefficient of x squared, so 2 times 1 is 2. We have negative 2, which is just 2 divided by 2, 1. Okay, so the x coordinate of our parabola is, the x coordinate of the turning point of the parabola is 1. And that's the point where we're going to split our domain into pieces. Okay, so just like we did with the previous example, we can write two rules. So the first rule will be g, and this would be the left-hand piece of that parabola. And you can think about the domain as being from negative infinity all the way up to that x value that we split our parabola to. Okay, so in this case, the x value is 1. So our domain is from negative infinity to 1. But our rule is still the same. Okay, our rule is g of x equals x squared minus 2x plus 4. Okay, you can do the same thing for the right-hand piece of this parabola. Okay, the right-hand piece is going to have a domain starting at the place we split it, so starting at 1, and going off forever to the right up to positive infinity. So we'll have our domain as being from 1 to positive infinity. And our rule, same parabola, x squared minus 2x plus 4. Okay, so now we've written two separate functions so that if we were to draw both of these functions on the same Cartesian plane, you'd end up getting a graph of the entire parabola. Okay, I'm going to show you what that looks like in Desmos so we can actually prove whether or not this is actually a correct thing. So let's go to Desmos. All right, so let's type in our equation of our parabola. So we'll go y equals x squared minus 2x plus 4. Okay, so that's what the original parabola looks like. All right, so let's hide that for now. Let's type in the left-hand piece. Now, Desmos has a funny way of writing in domains. So basically, we just have to write the rule. And in curly brackets next to it, we write our domain. So I'll go x is less than or equal to 1. And it gives me the left half. Okay? So that's the left half of the parabola, where the domain here of this function that we've drawn is from negative infinity up to and including 1. Okay? So that would correspond to this function here. I can do the right half by just changing the domain specified by these curly brackets. So same rule, except our domain is now x greater than or equal to 1. Okay, and you can see the two parabolas halves join up at that point, and they are exactly the same as the original parabola, which I can now show and hide the other two. There it is. Okay, so cool. It's really neat that we're able to do something like that. Okay, so you can split your parabola into two functions with separate domains, restricted domains, so that each function is one-to-one. All right, cool. So we'll stop there, and I'll see you in the next video.